This morning, I actually changed the lecture as I was listening to the talks this morning. I'm going to talk a little bit about the early Mars climate problem, essentially the faint young sun problem on Mars, which is much more difficult than the faint young sun problem on Earth. And then I'll talk a little bit about the outer edge of the habitable zone, sort of following up on what I did the inner edge last time on Venus. But I'm going to go through that at a fairly fast pace because what I'd like to bring us back to is try to tie together what John was talking about with the biogenic gases that get released into the atmosphere, and what Jonathan was just talking about is these future direct imaging missions where we would hopefully do spectroscopy of exoplanet atmospheres and just get us thinking about what gases we might be able to observe and what they might tell us about the presence of life. Because that to me is really the central question, astrobiology question for the astronomers who are interested in planets outside of our own solar system. Before I do that, there was a question that I think Elaine asked yesterday about whether the Earth could experience a runaway greenhouse as a consequence of adding CO2 to its atmosphere. And I mentioned that we had done a paper on that 25 years ago now, which came out in Science. And these are the calculations here. In this case, we just took the present Earth and added, instead of just adding the fossil fuel reservoir, we added 100 bars of CO2 to bring it up to Venus-like CO2 levels. And just put that into the climate model. So and we did calculations for present solar luminosity and also for 70% solar luminosity. Because it's actually relevant for the early Earth. If you bring in the entire carbon inventory early and degas a lot of that into the atmosphere, the early Earth could have had an CO2 atmosphere with maybe not 100 bars, but several tens of bars of CO2. And so the question is, would you get a runaway greenhouse in either case? And the answer is no. So if you add all that CO2 to these, those two different luminosities, you can get surface temperatures on the order of 500 Kelvin. But as I said last time, you never get boiling because you're increasing the surface pressure as that goes along. One of the things that stabilizes it is that the planetary albedo goes way up as you add that CO2. And I said this last time, that's because CO2 is a very good Rayleigh scatterer. Its Rayleigh scattering coefficient is 2.5 times that of nitrogen oxygen. And so you get a lot of diffuse reflection of sunlight as you make that atmosphere dense. Just on that thought, Venus has an albedo of 80.8, and it's generally considered that that's because of the sulfuric acid clouds. But if you take the sulfuric acid clouds out of Venus, it still has an albedo of 0.6, just because of the CO2. So that's a very stabilizing influence. The bottom panel here shows the saturation water vapor mixing ratio at the surface. And I didn't really go through this carefully last time, but that's what controls how much water gets up into the stratosphere. Andy Ingersoll wrote a paper back in 1969 showing that if you get more than about 20% water vapor by volume in the lower atmosphere, then you get that extended troposphere and you wash out the cold trap. So the other figure in this paper was actually on stratospheric water vapor. This is for a present solar luminosity. This was the surface water vapor mass mixing ratio on the left, which gives you about 10%. And then the curve that's relevant is this dashed one. That's stratospheric water vapor, which is for today's CO2 level, it's low. It's on the order of a few parts per million. It actually goes through a maximum there at a few tenths of a bar of CO2. You get the stratosphere starts to become wet. So the Earth would be on the verge of losing its water. But then as you put more CO2 in, it actually stabilizes the surface because the surface pressure goes up faster than the temperature does. And so the Earth is stable against the runaway greenhouse or against loss of its water. And so the point there is that if a planet is in the habitable zone, it's actually pretty stable. But if you move it, as we saw last time, if you move it a little closer to the sun, then that's not true. All right, well, so that's just says what I just said, that the Earth is stable. Now let's think about the outer edge of the habitable zone. And the outer edge of the habitable zone is very much like, trying to understand Mars' early climate. Now, Jonathan talked about Mars yesterday or the day before, and he showed you some pictures of Mars and talked a little bit about water on Mars. We have known for a long time that there was water on Mars' surface. It goes back to Mariner 9 in 1971. But a lot of the best images come from the Viking missions. Viking got there in 1976. And, Viking was an old spacecraft. It was not nearly as high resolution as today, but in a way that's good because the Viking imagery covers the whole planet. And if you get these high resolution cameras that we're flying these days, you only image parts of the planet at a time. So if you really want to see features like these fluvial features, the Viking images are the best. The Viking frames are about 200 kilometers across. You see things like this. This is what's called an outflow channel, where it's a massive flood feature is how this is interpreted. In some manner, there was a lot of water that was released from this area right here, and it flowed down to the right. That channel is about 40 kilometers across, so this was a huge flood feature. Here's another outflow channel, Ares Vallis, and here you can see a teardrop-shaped island that formed around that crater. So that crater was here before the flow came, and then the flow went around it and formed this feature, which is obviously fluvial in origin. You also see channels like this. These are called runoff channels, or just valleys today. Again, it's 200 kilometers across. This doesn't look like a flood feature, though. This is a much narrower valley. It has these short, stubby tributaries, which puzzled people for a long time. But the interpretation is that water, instead of just flowing over the surface, as it does on Earth, on Earth, river systems are very highly dissected. You have small streams running into bigger streams, and so the whole surface is covered with channels. Here, the water probably percolated into the surface and ran off subsurface. The process is called sapping, and then it collects in these channels and flows down. You see this actually in desert areas today. You can see this same type of feature. And just thinking about the life connection, I think it may be because there was no organic material in the soil. If Mars, the surface was not inhabited, and so the soil was much more porous. It was much like sand instead of like dirt as we have here on Earth. Dirt has a lot of organic carbon in it. And then finally, this one more picture. This is what's called a valley network. These are also valleys, but this one looks a lot more like a terrestrial river system. This is the best valley network on all of Mars. It's Warrego Vallis. And here you see lots of channels flowing into a main one. And then if you kind of squint, you can see this might be the shoreline of an ancient lake or ocean. So all of this is now and has always been considered evidence that water flowed on Mars' surface. Now, how do you get that to happen? In spite of the fact that we know that the water flowed on Mars' surface, there's been a big debate about the climate of early Mars, because there are some people that think you can do that with a cold Mars, and there's others, including myself, who think that it had to be pretty warm in order to form those fluvial features. On the cold early Mars model, the model that's gotten the most attention is the impact model, which was published by Teresa Segura, Brian Toon and colleagues at University of Colorado. And so their idea was that Mars was cold all the time, but then you got these big impacts that came in during the heavy bombardment period, and they would vaporize a lot of ground ice, and there was water ice in the impactor, and then you create a temporary steam atmosphere, and all of that water would then, the steam would then condense out, and those fluvial features were formed by the rain out of these impact-induced atmospheres. Well, I don't think that model works, and you can test it sort of in this back-of-the-envelope way by looking at some of the more recent images here. This is now one of these valleys. It's Naneti Vallis, and this is from a more recent spacecraft. This is Mars Global Surveyor, which has one of these really high resolution cameras that they're all built by the same guy. It's Mike Malin, who used to be at Arizona State, and he got so successful at building cameras for NASA that he formed, I think it's Malin Incorporated, and all he does is make high resolution cameras for Mars missions. But he's
I have to say that the high resolution camera on the Mars Reconnaissance Orbiter, HiRISE, was built by Lockheed and PI's Alpha.
Oh, so there's somebody else got onto a Mars mission.
It's not Malin Space System.
Oh, okay.
It's a large format camera and it's sub-meter resolution.
All right. Well, Malin's been on any number of Mars missions.
Plenty of business.
Right. And so this is a Malin picture here. What you could see, and this one got a lot of press when it came out, that channel is about 1 kilometer across because the frame is 3 kilometers. You could see the valley is 1 kilometer across. What you could see here that we could never see before was the river channel cutting through that. And we thought these things were cut by rivers, but you could never see the river. The river's maybe 30 or 40 meters wide down there. How many people have been to the Grand Canyon in the U.S.? I mean, this looks a lot like the Grand Canyon, actually. If you've ever been there, the Grand Canyon is 1 mile wide and 1 mile deep, and the Colorado River is about 30 meters wide down at the bottom. This thing is not quite as big as Grand Canyon, but almost. So you can make analogies as to how much we actually know a lot about how much water it took to form the Grand Canyon, because we know that it formed in a time scale of about 17 million years. That's the time scale for the uplift of the Colorado Plateau. And then I just did a little back of the envelope calculation. You take the mean annual rainfall over the Colorado Plateau, most of which flows out through Grand Canyon. You get it's about 30 centimeters a year. So in 17 million years, you would have 5 million meters of rain that fell on the Colorado Plateau. And so that's about what it takes to produce something like that on Earth. In the impact hypothesis, they're saying that you could form features like this with 50 to 500 meters of rain. So I think they actually missed the ballpark by a factor of between 10 to the 4th and 10 to the 5th. And that's why I don't believe these cold early Mars models. I think it has to be warm enough that you have a hydrologic cycle like Earth, so you actually get rainfall over a long period of time. But that's posed this problem that's, I think of as the faint early sun problem for Mars. We should be able to explain that then with the climate model, why the climate was warm, and it's been very difficult to do that. The thing that would, that we all pretty much agree on is that Mars was geologically active, it was tectonically active early in its history, and so these same cycles that I've been talking about for Earth would have operated on Mars. And the one that I've talked about extensively here is the carbonate silicate cycle. So let's assume that Mars had a lot of carbon to begin with, which may or may not be true, but if it had an Earth-like abundance of carbon, and it had some kind of tectonism, plate tectonics, or at least volcanism, then you would get cycling of CO2. And if Mars was too cold, then the CO2 would build up in its atmosphere, and it should get enough to increase the greenhouse effect, just as on Earth. So we can, today Mars' atmosphere is very thin. It's only about 6 millibars, but most of us agree that CO2 must have been higher back in the past. There's lots of evidence for volcanism on Mars. Mars has the biggest volcano in the solar system. It's Olympus Mons. And that thing is 30 kilometers tall. It's just a huge structure. Mountains can be higher on Mars because the gravity is low and the crust is thick because the interior isn't as hot as Earth's. But this is part of the Tharsis Bulge, which actually has 3 huge volcanoes on it in addition to Olympus Mons. So there's no problem with volcanism early in Mars history. Now, I've worked on this problem on and off for a long time. These were some calculations that I did in 1991 where we tried to warm early Mars up with CO2. take the climate model, and in this case we had a pure CO2 atmosphere, and we were calculating surface temperature for 4 different values of the solar luminosity. In this model, if you take present Mars and add about 3 bars of CO2, you can get above the freezing point of water, and you can still do that at 90% of present luminosity. But if you get down below about 85% of present luminosity, then you don't get there, for reasons that I'll explain in a moment. These channels, we think, I showed you those pictures. All of those valleys, or most of them at least, are on heavily cratered terrain. And the interpretation there is that they formed during the heavy bombardment period, which we think ended by about 3.8 billion years ago. Solar luminosity at 3.8 billion years ago was 75% of the present, according to Gough's solar evolution curve. So the goal for us climate modelers for a long time has been to try to make Mars warm at 75% solar luminosity. And that's about where this red dot is. That's as warm as you can get in this model with a CO2 water atmosphere, 225 Kelvin, which is still 50 degrees below the freezing point of water. And to me, that's a big problem, because the whole planet, if there's a lot of water on Mars' surface, it would be snowball Mars, just like snowball Earth, and you wouldn't have a global precipitation cycle, so you wouldn't be able to form those valleys. So that's been the problem for a long time. Why can't you warm it up? It's for 2 reasons. One is that when you're farther from the sun like that, CO2 begins to condense, just like water does in the Earth's atmosphere. And if you look at these temperature profiles, as you increase the amount of CO2 in this model, this is for going from 1/10 of a bar of CO2 up to 5 bar atmosphere. We're following moist adiabats in the troposphere, as I described last time. But now you've got 2 types of clouds that are forming. In the lower atmosphere down here, H2O would be condensing, and you would get H2O clouds. And then you can see there's a change in the slope up here, and that region up there is where the CO2 condenses out, and you'd have CO2 ice clouds that were forming in that atmosphere. Well, that actually cools the surface temperature in one respect, because anything that lowers the lapse rate lowers the greenhouse effect, because the stratospheric temperature is essentially pegged there by radiative equilibrium, and if you had a steep lapse rate all the way down to the surface, then you would get a high greenhouse effect. If you have condensation like this, then you get a lower lapse rate, and so you get a lower greenhouse effect. And then the other thing that keeps the CO2 from warming it up is what I already mentioned, that CO2 is a good Rayleigh scatterer. So as you try to up the CO2 pressure in the atmosphere, the planetary albedo goes up from about 0.3 in this model up to more than 0.6. A dense CO2 atmosphere reflects most of the sunlight that hits it. And then the last climate calculation I'll show you, you can do inverse calculations for Mars, just like you can for Earth. In fact, this is what we did in the paper on the habitable zones. We just in this calculation, we held the surface temperature of the planet at the freezing point of water and simply pumped up the CO2 partial pressure and calculated these fluxes that I described last time. Fs is the solar flux at present solar luminosity, and FIR is the outgoing infrared flux. This curve shows the albedo, which increases as you increase CO2. And then down here, this is the effective solar flux that you need to maintain the surface at the freezing point of water. And it has this interesting behavior. It's a dish like that. It's concave. And so this is what we call the maximum greenhouse limit. That's where you get the maximum warming out of CO2 at a surface pressure of about 5 bars. Now, why is that? It's because if you're at low CO2 levels, then you get a low greenhouse effect and you have a low albedo. So it's relatively cold. As you go to high CO2 levels, you get a big greenhouse effect, but you also have a big albedo. You're reflecting most of the sunlight back to space. And so the optimum is somewhere in the middle there at 5 or 6 bars for Mars. And that's the outer edge of the habitable zone. That's as much warming as you can get out of a CO2 water atmosphere. And we've experimented. You can put some methane in there. It doesn't really matter that much. So this is what defines the boundary, the outer edge of the habitable zone in our models. So let me put up a picture of the habitable zone. Then Jonathan put up a different one earlier. I like this one. This one is not my diagram. I snatched this off the web. Somebody is much more artistic than I am. So this is a really pretty version of the habitable zone. It's obviously from somebody over here in Europe because it has commas instead of decimal points. And it's really, this is distance in AU. This is the zero-age main sequence habitable zone. The one that Jonathan put up was actually the continuously habitable zone, so it had time factored into it as well. Here you're just looking at zero-age main sequence. The habitable zone is a nice bright blue for liquid water. Earth at zero-age main sequence was sitting right in the middle of the habitable zone. We're sort of towards the inner edge today because that habitable zone is moving outwards with time. And in another billion years we'll be beyond the inner edge according to our model. Now while this is up here, there's problems for stars other than the sun. If you go to the bright blue stars, then the habitable zone is plenty wide, but the main sequence lifetimes are much shorter, so you have less time for life to evolve. If you go to the M star, late K and M stars, you get within the tidal locking radius of the star, and so the planetary rotations may become captured and you get synchronous rotation, which may or may not be a problem. The other thing that I would point out is that in log space, if you have distance on a log scale like this, the habitable zone is about the same width for all types of stars. And so if planets are spaced geometrically as they are in our own solar system, then the chances of getting a planet within the habitable zone are about the same for all different types of stars. The geometric spacing of planets is something that's been known for a long time. It's called the Titius-Bode law. And it was scoffed at for a long time by astronomers because it was just simply a mathematical progression, but it's related to dynamical stability. These orbits are stable, and this solar system is our own solar system is packed. You can't stick any more planets in there between the other planets. So we will see. I mean, so far we haven't seen any other solar systems that look like this, with the possible exception of that one that Jonathan showed, the Kepler system, that's very small, but you get geometric spacing of the orbits very tightly in, and it's for dynamical stability reasons. The M stars, I think I'll come back to this next time. In the near future, it's hard to look at the FGK stars, as Jonathan already mentioned. We may be able to look at M stars earlier with JWST, although I've been told by people from JWST that it is very difficult to get a transit spectrum of an Earth-like planet in the habitable zone of an M star from JWST. So if they're lucky, they may be able to do it, but there are no known transiting M star systems right now for which you could make a good transit observation. That said, the M stars are interesting because they're the first ones we can look at. There are a litany of potential problems for habitability for planets around M stars, one of which is the tidal locking, although you can get around that problem if the atmosphere transfers heat around to the night side. These planets may not have magnetic fields. Helmut Lammer has written about this in papers. If they're synchronously rotating, then they're not, depending on their orbit period, they're not rotating very fast, so they may not generate magnetic dynamos within their cores. And then in Helmut's calculations, he does model atmospheres and tries to calculate how much loss of atmosphere there is from interaction with the stellar wind. In Helmut's calculations, most of these M-star planets lose their atmospheres. partly because they don't have magnetic fields, and partly because these M stars are pretty active, and so they can have very intense stellar winds.
Jim, what
Yep.
an interesting variant of tidal locking is what Mercury does. We have a spin orbit resonance where you do actually get a whole phase.
Right, thank you. Mercury's in a 3-to-2 spin orbit resonance, so that's another way out of the tidal locking.
And it requires a whole permanent quadrupole mode to get it into this state.
Right.
So you
So,
have to live on a lumpy planet. In other words,
Exactly, yeah, and it comes to this.
yeah, and Rory Barnes at University of Washington points out that just because you're tidally locked doesn't necessarily mean that you're synchronously rotating. Even, you don't have to be as misshapen as Mercury is. If you have other planets, then you can get caught in various resonances. So I think we'll just have to observe planets in order to see what actually happens. And then finally, there was a paper by Jack Lissauer 4 years ago now where he points out problems. One of the biggest problems is these, the habitable zone around M stars is very close in. There's not that much material around there, so you may not form big planets unless bigger ones migrate in. And Jack also suggested that it may be harder to get water to these planets because the ice line in the nebula is actually farther away from the habitable zone in an M-star system than it is in a G-star system. And we can come back to that. I don't think M-star planets are the best place to look for life, but I don't think they're impossible either, and they're probably the best targets in the near future. While we're on habitable zones, there are some mega concepts of habitable zones, and I just wanted to mention this one, the galactic habitable zone. I think Jonathan may have mentioned it earlier in the week. This is a diagram from Charlie Lineweaver and colleagues. And so they're trying to calculate the region in time and space in the galaxy which is habitable for complex life. And you can do this for simple life, you can do it for intelligent life. This particular figure is relevant for complex life and intelligent life. So it assumes that you have to be around for 4.5 billion years in order to get smart animals to evolve. The way they've graphed it is galactocentric distance in kiloparsecs versus time before present with the sun right here, because the sun this is when the star forms. So the sun formed 4.5 billion years ago, and it's right, this green region is what they would say is the optimum place in the galaxy for evolving intelligent life. I can see objections already arising from the audience. If you're too far out on the disk, it's too metal poor. If you're too far in, there's too many supernovas. I put this up mainly to stir up a little controversy. It's an interesting concept. It's not that relevant to the near future because what we're interested really is looking in the solar neighborhood. And the solar neighborhood is probably smaller than that little dot that represents the sun. So at least for the present, we're going to be right in the green area of this diagram. And we can come back to this as to whether this diagram has any meaning, but it's kind of fun to show it. As I just said, and Jonathan was talking about this earlier, with these direct imaging missions, which we call Terrestrial Planet Finder in the US, we'd like to look out to the nearest 10 to 15 parsecs, and then we want to look for spectroscopic signatures of habitability and life. So I went back and thought about the list of gases that you put up the other day, John, biogenic gases that come off of potential biospheres that we might be able to look at. The most obvious one, of course, is oxygen and its photochemical byproduct ozone. So that's for a planet like the Earth. Methane, I've talked about a lot, and John has talked about. There's also nitrous oxide, N2O, which comes from denitrification and is present in Earth's atmosphere at about 0.3 parts per million. John, you mentioned H2S from some forms of sulfur metabolism. And then there's actually a host of other biogenic sulfur gases, carbonyl sulfide, dimethyl sulfide, and carbon disulfide, which are produced mostly by marine algae. Well, people have actually been thinking about this. I'm part of Vicki Meadows' group at University of Washington, and we've sort of been working through this list of gases. In order for them to be useful for TPF, they not only have to be produced by a biosphere, but they have to build up to enough concentrations in an atmosphere in order to be visible spectroscopically, and they have to have an absorption band that is in the range that you could see with either an optical or an infrared type of TPF mission. So unfortunately, for the near future, the only ones that we think are likely to see are oxygen and ozone. I'll show you. Those are pretty easy. Methane is easy on early Earth type planets, but it's very difficult on the present Earth because it's only 1.6 parts per million. N2O is almost impossible to see. If you go back in time, actually N2O gets worse because if you take out the ozone layer, then N2O photolyzes quickly. So even if you were producing it fast, it wouldn't be present. H2S has a problem that comes out of volcanoes. This was a similar problem for methane. You get a lot of methane from serpentinization. So if you saw either H2S or methane, well, maybe that's from life, but maybe it's from physical processes that we already understand on our planet. And then finally, these other biogenic sulfur gases, those would be great if you could see them, but one of my former students, Sean Domagal-Goldman, who's a member of Vicki's group, has just submitted a paper to Astrobiology where he put all of these species into an early Earth model. You don't see them in the present Earth, but we wanted to see if you could see them in an early Earth model, and they all photolyze too fast, so they don't build up to high enough concentrations.
So what about hydrocarbons, volatile hydrocarbons beyond C1 methane?
Well, in the present Earth's atmosphere, which is oxidizing, they're in low concentrations. In the early Earth, I showed you, we make those things photochemically. That's what makes the haze through polymerization. So I don't think they would be, they're indicators of methane, but
could there be some ratios that might be an indication?
Actually, Sean's paper says you may get more ethane. I mean, it's a convoluted argument. If you have all these biogenic sulfur gases going in, you may get an increase in ethane, and then indirectly you might be able to infer something. But it's a really it's a weak argument, frankly. Even I can say that because I'm a co-author on this paper. So let me show you. Before I forget, what would be the best spectroscopic signature for life? What you'd really like to see is the simultaneous presence of both an oxidized gas, either O2 or O3, and a reduced gas, either methane or N2O. This was suggested a long time ago, back in the 1960s. There were two papers that came out in Nature the same year. One was by Joshua Lederberg, who's a Nobel Prize winner, and he suggested that the signature, the best remote signature of life would be the simultaneous, would be the detection of extreme thermodynamic disequilibrium in a planetary atmosphere, just a general concept. And then that same year, Jim Lovelock, who's the author of the Gaia hypothesis, proposed that what you'd really like to see is the simultaneous presence of oxygen and methane, because those gases in Earth's atmosphere are out of thermodynamic equilibrium by about 20 orders of magnitude. They're both produced primarily by biology, the O2 from photosynthesis and the methane from methanogenesis. So that is considered the holy grail of life detection. And eventually we may be able to do it, although I'll show you it's very difficult right now.
But you also told us that you can photolyze water, get the hydrogen go away, and keep an oxygen-rich atmosphere without any biological activity.
Yes, thanks. So I missed my bullet here. Leftover O2 from a runaway greenhouse.
Which then means that none of that is a clean signature for life.
Well, but in a way that's right, but if you know, this is why you need to know where the boundaries of the habitable zone are. Because if for a planet like Earth that's sitting safely within the habitable zone, you don't lose water abiotically. You know, I just went through that. But for Venus, you do. So if you know where that inner edge of the habitable zone is, you can tell whether it's a runaway greenhouse signature or whether it's a signature of life.
And for that, you need a very big confidence in all the models that you've been describing.
Well, or you need a bigger spectrometer, a bigger telescope, so that you can look for other things like methane along with it, right? So, you know, you're right. Oxygen and ozone are ambiguous biosignatures by themselves, although we think we can say something from that. But they, you know, if you see those, then you can do the big mission, the really big mission after that, and go after this simultaneous detection criterion.
If you follow that argument, wouldn't it be more fruitful to start with questions which are less related to life and more to the planets, and then see what you learn from that, and then ask the life-related questions?
Well, I'll show you. You get both at the same time. So if you're looking for evidence of habitability, one of the things we want to see is water, or at least water vapor. You get the biosignature gases at the same time. So you really, and so I'll do this quickly because some of you have probably already seen this. You can do a TPF mission in the infrared. Of course, the people who have worked on it hardest are over here in Europe. Alain Leger was the head of the Darwin project for a long time. Darwin's not going to fly, but it should fly at some point because you fly a free-flying set of spacecraft and make a big interferometer. This is a good way to look for planets. In the US, we think it would be very expensive because you need 4 or 5 spacecraft doing formation flying, and they have to be cooled so that you can work in the infrared. If you could do that, though, here are the infrared spectra of Venus, Earth, and Mars at fairly low spectral resolution. And if you look at Venus and Mars, all you see is that 15 micron band of CO2. That's this one that gives us the greenhouse effect. But with Earth, I already showed you a different version of this. This is the Earth spectrum from a distance. And you see that ozone band at 9.6 microns. You see the CO2 band, and you see these water bands that I talked about earlier. So this is what I was just saying. You know, if you get this spectrum, sure, you look for water, but there's ozone sitting there in the middle and makes you wonder about life anyway, even if you're not confident that it's there. In the US, where NASA's very much thinking about doing a TPF type mission in the visible near IR. This was a project TPFC, the C is for coronagraph. We were working on that very hard about 5 or 6 years ago, and then all of a sudden the money ran out for it. But this, one way to do it, you need at least a 4-meter telescope. You have to have a very good coronagraph on it so that you can block out the light of the star and look for the planets very nearby. There's another version of TPF in the visible, which people are thinking about very seriously. It's an occulter version of TPF. And so the Webb Cache at University of Colorado had a mission that was proposed called New Worlds Observer. In this one, you have a 4-meter telescope here, and then you fly a big occulting disk that actually looks like a flower because it's got petals on it. Those are for apodization, basically. And you fly that at about 50,000 kilometers from the telescope, and then you just block out the light of the star with it. Just like if I wanted to block out that light, I put my hand in front. The optics on that are really simple compared to a coronagraph. And you have to do formation flying, but on the other hand, your telescope mirror is greatly simplified. It only has to be about as smooth as the Hubble mirror. Whereas if you do the internal coronagraph, your primary mirror needs to be 20 times smoother than the Hubble mirror, which you can't grind them that smooth. You have to do that with actuators and whatnot. So the mirrors are a real problem on the coronagraphic missions. And then finally, my last slide is what do you see with if you look at Earth with a telescope like that. It was a little tricky to figure out how to get an Earth spectrum, but Nick Wolf and group at University of Arizona figured out a clever way to do that. You look at Earthshine data. If you look at the moon at night, when it's in crescent phase, you see the bright side of the moon, which is illuminated by the sun, but you also see the dark side. You can see that by eye on a dark night. Where is that light coming from? It's hitting the Earth, then hitting the moon, and then coming back. So it's got an Earth spectrum embedded in it, and if you subtract out the day side spectrum of the moon from the night side spectrum, you get the Earth spectrum. It's called an Earthshine spectrum. These are the data that they took from this initial one right here. That black curve is the Earth spectrum in angstroms here, and you can immediately, and then this red curve down here is their model fit to that spectrum. You can easily pick out several things. You can pick out these water bands right here. There's a broad ozone feature there, which actually may not be that easy to detect because it's so broad. But then right here at 7,600 angstroms, or 0.76 microns, that's the O2A band. That's one of the strongest features in the Earth's visible spectrum. And so you could pick that out on the Earth if you had a spectrometer with a resolution of about 70 or so. So let me just finish up then with some conclusions. Early Mars could have, I said it was difficult to warm it up. There's actually a young guy in Britain named Robin Wordsworth who's figured out how to do it. He's running 3D climate calculations with CO2 clouds in there, and you get a warming effect from the CO2 clouds, which I didn't have time to talk about. So that's probably possible to do. As I said, habitable zones around FG and early K stars are probably relatively wide, because, and it's all because of that negative feedback in the carbonate silicate cycle. That's what makes the habitable zone wide in our models. The M stars have good continuously habitable zones, but they have other problems for habitability. And then finally, within the next 20 years, hopefully while I'm still alive, it would be really fun to do one of these TPF missions and look for evidence of Earth-like planets and life. Thank you.
Also from the lecture that volcanism and tectonic sulfurology is important, and so it should depend on the mass of the planet, so there should be a dependence on the mass of the planet of the habitable zone, right?
People have tried to then put the planet in there and try to calculate the dependence of the habitable zone on planetary mass. There's a group in Germany, Frank and colleagues have been doing this. They've published 5 or 6 papers where they try to do exactly that. And they have what they call their dynamic habitable zone. They run planets of different sizes, and they all have their own different habitable zones. But, to me, it's taking the calculations a step too far. For one thing, you have to include a lot of parameters that you don't understand. And for another thing, you don't know the masses of these planets beforehand. So at least for now, what you want to know for now is where should you be looking around other stars. And the models that we've done are fairly mass independent. You can do those same calculations. If you look back at our 93 paper, we did them for 1 Earth mass planets and 1/10 of an Earth mass, so like Mars, and for 10 Earth mass planets. And the boundaries of the habitable zone don't actually change that much in our models. They do change in Frank's models because he's trying to evolve the planet, and he's building in a lot of assumptions about the carbonate silicate cycle and plate tectonics, things that we don't know very well. Yeah, Deborah.
What about the impact of the late heavy bombardment on Mars? Do you think that would have been sufficient to sort of make this cold Mars scenario work?
Well, what that late heavy bombardment can do is that if you've got carbonates in the surface, that's a good way of volatilizing them. So that's another way of recycling CO2 back into the atmosphere. But the direct effect of that, that's what these impact people have, like the Segura et al. Group, they've been trying to directly warm Mars up with those impacts, or at least explain the valleys, and there's just not enough energy there to do that. I don't think. Yeah.
Is it clear that water is the only volatile which could have created these rivers on Mars?
There have been lots of, the question is, can it be anything other than water? There was a paper back in the 70s suggesting it was liquid alkanes formed from polymerization of a methane atmosphere, so that'd be sort of like Titan. That really doesn't work if you go through the numbers on it. There are suggestions it was liquid CO2 that did it, but the triple point pressure for CO2 is 5 bars and 216 Kelvin, so you need more than 5 bars, and actually we've looked at that radiatively. That doesn't work either. So actually we're pretty sure it's water. Other things have been considered.
Well, the measurements of hydrogen and hydration from some of the recent missions indicate that there's ice water. Very
So that's a better answer. We have ground truth evidence from the rovers, and it was water. Yes?
By designing these missions to look at what we think is the habitable zone, don't we risk to miss some other very interesting objects, different properties?
Yeah. Okay, so that's really a key question there, is are we being too restrictive by looking in the habitable zone? But I would say not. For one thing, if you design your instrument to be optimal for looking in the habitable zone, it doesn't mean you can't see elsewhere. And so if we stare at a star, we're going to hopefully see the entire inner solar system. In fact, for TPFC, we had a requirement on it that it be able to see out to 10 AU around a G star, so that you could catch Jupiter if it was out there. And actually Jupiter's at 5 AU. We had the requirement at 10 AU, so you'd be sure to get Jupiter. So you will see other things. For the indicators of life, I think you do have to be conservative. I think you want to be looking in the liquid water region, because suppose you're not there. I mean, suppose you're out at 10 AU and the solar flux is really long or really low. What are you going to look for? What's your evidence of life going to be? Extreme thermodynamic disequilibrium between what gases? You have to make up a metabolism. I think you really want to be conservative about this and look in the liquid water region. Yes?
I just wanted to comment that this some form of geometric assembly of the planets have been detected in several low mass systems even before Kepler-11. And even that when the bigger the mass of the planets, the wider the relative spacing seems to be, which is also in agreement with theory, which is good news for these M planets.
Yeah. Yeah, there's some old papers on habitable zones. There was a guy named Huang who worked on this concept back in the 1950s, and he said that the habitable zone around an M star was so narrow that you wouldn't find planets there. But he was thinking, in linear units, not in logarithmic units. So in logarithmic units, the habitable zone around an M star is just as wide as it is around a G star.
So Jim, I think a lot of our whole concept of habitable zones is what is expressed on the surface of a planet or a planetary body. And I think you can go even into our solar system and go beyond that. The classical habitable zone into zones of liquid water and maybe lots of the activities that would generate life in the subsurface. And that's one of the reasons we go to icy moons.
Yeah.
And so what really is the habitable zone if we just don't restrict ourselves to surface expression, but we are interested in subsurface expression?
For remote life detection, that habitable zone needs to be at the surface because these organisms have to be modifying the atmosphere in a way that you can detect it. You can't see life on a distant Europa. There's just no way to do it.
But when we're talking generally about the habitable zone, it'll be really interesting to include icy bodies that have liquid water and some that have potential rotations that could indicate a source of heat generated. Otherwise, why go to Europa?
Oh, well, in our own solar system, you just go look. Right? Okay, so I think you're all ready for the break. So, thank you.